Now we're going to take a look at the exponential functions, which are the functions that are in the form 2 to the x power instead of having x squared. So these are the functions where the variable is actually the exponent position instead of the base. Before we go into the new content, it was worth doing a quick reminder on a few of the most commonly missed or forgotten exponent properties. So don't forget that if you have a radical, then that can be written as a fraction exponent. We will frequently be using this property. For example, if you have the third root of x squared, the exponent on the inside of the radical is the top of the fraction exponent, and the index is the bottom. So x to the 2/3 power, you'll need to be able to rewrite radicals that way. Also, it's important to remember the negative exponent ones. These are essentially the same property. If you have a negative exponent, then it's the reciprocal of that base. So if you have something like 2 times x to the negative third power, do note that the negative exponent is only on the x here, so the 2 is not being affected. So this stuff is over 1. The 2 stays where it is because it does not have a negative exponent, but the x to the negative third power flips down to the bottom of the fraction instead. So only the bases that have a negative exponent will flip, and then this is showing the same property the other way around. So if you have that negative exponent and it's already on the bottom of the fraction, then it will flip to the top. But again, the other numbers and bases that do not have negative exponents will stay where they are. So the 5 stayed on top since it was not affected by the negative exponent. So here is our formal definition of what an exponential function is. It should be in the form a times b to the x power, where a and b are both real number constants. So that means we shouldn't have any imaginary numbers. And it means the a and the b values, they shouldn't be variables. You should have set numbers for them like 2 and 7. A is what we will refer to as the initial value. So when we're doing population models, it might be what is the population of the city before we start looking farther into the future. And then b is the more important number here. B is the base of the function. So it's what's being raised to the x power, or they might use a different variable like t. It doesn't really change much there. Now, one comment about this is sometimes you may not see a number being multiplied out front, and that just means that a is 1. Because if you have 1 times something, then you don't need to write that part. So if you don't see a separate number being multiplied by a number to a power, then a is 1. Now, there are two different cases for the b value. There's the case where b is bigger than 1 and the case where b is less than 1. You'll notice for both of these cases, we're specifying that a should be bigger than 0, which means a positive number. So we're really just talking about what happens when all of these are positive for now. So if b is bigger than 1, what's happening is we're multiplying by a number like 2 over and over and over again. So it keeps increasing the size of the population, or maybe how much money is in a savings account, for example. However, if that b value is less than 1, so if it's a fraction like 1/2 or 1/3, then it's taking that amount of money you have in the bank account, and as time goes by, it's cutting it in half, cutting it in half again, cutting it in half again. So it's getting smaller and smaller on the right-hand side. So these are the basic shapes of what you should recognize for exponential growth and exponential decay. So now let's look at some specific examples using exponential functions. One thing you will be asked to do is compute an exponential function using a specific x value. So they may just give you the function and say plug in x equals 3, or it may be more of a word problem where they give you a population model and they say find what the population is 20 years later. So you're plugging in 20. In this case, I'm just going to have 7 times 2 to the 3rd power. Now don't forget to always use your PEMDAS rules. So before we multiply, we do have to do this exponent here. So 2 to the 3rd power is 8, and then 7 times 8 is 56. So this was basically just a matter of substituting the number in and then simplifying the expression. Sometimes they may give you a couple coordinates, or they may even give you a table with lots of coordinates, but we really only need 2 of them, and ask you to write the exponential function. So we're going to be looking for 2 values here. We're going to be looking for the initial value, and we're going to be trying to figure out what they multiply by to go from term to term. Now, to find the initial value, that'll always come from what happens when x is equal to 0. So in this case, when x equals 0, a is equal to 4. Now, the b value can be a little bit trickier, but when you have x equals 0 and x equals 1, this is kind of the ideal case. We just need to figure out what did they multiply by to go from y coordinate to y coordinate. So in this case, b must equal 3, and I'm getting that from doing 12 divided by 4. I'm trying to figure out what they multiplied by, so you could also do it as dividing the other way around. So now I know that a is 4 and b is 3, which means my function would be f of x equals 4 times 3 to the x power. So the initial value is when x equals 0. The b value is what did they use to multiply to go from x equals 0 to x equals 1. So what did they multiply the y coordinates by? Now those same ordered pair or table examples get a little bit trickier when they don't give you x equals 0 and x equals 1. If they jump to like x equals 2 or 3 or 4 for one of the later coordinates, we have a little bit of extra work on figuring this out. Now I do still have that a is equal to 3 given to me. So your initial value is the y coordinate when x equals 0. To find b, I'm actually going to write the function. So I know that usually we have y equals a times b to the x. But since they didn't give me the x equals 1 value, I'm going to plug in this x and y into those two spots instead. So that would mean that I have 48 equals 3 times b squared. Well, in this case, I can divide both sides of the equation by 3. And then I can take the square root of both sides of the equation. So that now I know what b equals, which means I can go back to writing my exponential function as a times b to the x. So you find your initial value and then use the second coordinate. If it's not an x equals 1 value, if it's 2, 3, or 4, or whatever, then plug the x and the y coordinate into that function so that you can solve for b and then write the equation with that. So now we're going to look back at our transformation rules again. We've done these before for things like sine, cosine, and tangent, but we also need to be able to apply these same rules to the new function, which in this case is 2 to the x. Now I'm using 2 to the x as an example, but you can also do this for 3 to the x, 4 to the x. It could be your fraction ones like 1/2 to the x or 1/3 to the x. So these rules will apply to all of the functions in this exponential form. Now, one of the rules we learned was that if you add a number to the function itself, then that shifts the graph up. So if we're applying that to the function 2 to the x, then that would be what happens if we have 2 to the x plus 1, for example. Notice I'm not writing plus 1 in the exponent spot. I'm adding it to the entire function 2 to the x. So this whole thing has a plus 1, which is what makes this a shift up 1. So don't confuse that with the case down here. If I had 2 to the x, and in the exponent spot, it said plus 1. So if you're specifically adding that 1 to the x value, that's what causes it to become a shift to the left instead. Similarly, you may have something like a vertical stretch, which would be if you had a number being multiplied out front, and that number is something like 3 times 2 to the x. So that's another example from this list here. And for another example, a reflection over the y-axis, that would be if you change the sign on the x itself, not for the whole function, so not in front, but just for the x, which is in the exponent spot for these. So this would be an example of a reflection over the y-axis. So I hope you can recall these transformation rules and apply it to the other functions as well. I just wanted to remind you quickly how these work and show you a couple samples for the new function. With that said, here is an example asking us which transformations are being applied to go from 2 to the x to the function 3 times 2 to the x plus 1. So going back to our rules, I see that we have a number out front being multiplied and we have a number being added into the exponent spot. So a number being added in the exponent spot, specifically to the x, and a number being multiplied out front. These are two of the ones I just showed as samples. That means we would write that there is a vertical stretch by a factor of 3 and a horizontal shift to the left 1. So here are those answers written out, and I figured it was also worth repeating that the horizontal motion, so in the exponential functions, it's whenever you have something happening to the exponent, these are generally backwards from what you expect. So don't forget that the plus meant it actually went left 1, contrary to what most people expect. And along those same lines, if you had like a 3 times x for the exponent, then that 3 actually means that it's being shrunk by 1/3, the reciprocal of that number. So the horizontal stuff is always backwards from what people expect. Now your last type of example will have you looking at a function and determining whether it's exponential growth or exponential decay, and then we will also be describing what's happening for the end behavior using limits like we did in the last unit. So first, let's identify the exponential growth or decay. If you compare this back to the original rules, I said we're basically looking at the b value to determine this. If the number being raised to a power is bigger than 1, we'll say growth. If it's a fraction like 1/2 or 1/3, we will say decay. So since our b value is a fraction between 0 and 1 here, that means we have an exponential decay function. Next, for the limits, the notation we used is to describe what is happening for the limit as x approaches negative infinity, which means on the far left-hand side of the graph for the function, and what is the limit as x approaches positive infinity, so what's happening on the far right-hand side of the function. Since this graph did not have any shifts, we're not moving any of the asymptotes we see here. So looking at the exponential decay function on this one, I can see that the limit on the left-hand side, the height it seems to be approaching, looks like it's going up forever on the left. So I'm going to say positive infinity on the left-hand side. On the right-hand side, it seems to be approaching an asymptote at a height of 0. So the limit on the right will be 0. If the function does have a lot of transformations being applied to it, especially the shifts and the reflections, then you may want to type the graph into a graphing calculator so that you can look at the shape of it and then just identify the height on the left side and the height on the right side to do that end behavior using limits part. And the last thing I wanted to prepare you for in this video is a symbol that may come up in your assignments. It looks like a cursive E because this is sometimes called Euler's number, Euler starting with an E-U-L-E-R for spelling. And this is a number very much like pi, which you guys have seen before. It just kept naturally occurring when mathematicians were dealing with exponential and logarithmic functions. So eventually they got tired of writing out this entire number over and over and over again. So they just decided to use this symbol to represent it, to save time and space on their work. The official origin, the exact origin, actually comes from evaluating this infinite limit here. But for most purposes, it's okay to just know that this is a number very close to 3. So when you see an E in your equations, just know that it's approximately 3, and you'll get a rough idea of the answer from estimating that. Your scientific calculator should have an e to a power key on it because we will be using that a lot in the class, and that way you'll be more precise with computing your answers. And that's all for this lesson, so I hope that was helpful.